Welcome to Lecture 9. In this lecture, we're going to get started talking about capacitors, which is a brand new chapter for us. We're ready to get started now on Chapter 26. This is all about capacitors and dielectrics and capacitance. We've already discussed capacitors a little bit. We talked about what they were. Now we're really going to get into it and cover them properly. So anytime we have two surfaces separated by a small distance, if the surfaces are charged, it means there's an electric field between the surfaces. One example of a capacitor that we know really well from everyday life would be touch screens. So the screens of cell phones and iPads and smartwatches and smart boards, those all work on a capacitor function. So the screens themselves are capacitors. So that's kind of neat. If you ask why we use capacitors, it's because they're a device that stores energy and it releases the energy when needed. It's why you're never supposed to open electrical devices. You know, if your DVD player is not working that well, you might be tempted to unscrew it and take it apart. You're not really supposed to do that. And the reason you don't do that is because there's a bunch of capacitors inside that have all kinds of electrical energy stored. And if you hit one of those with your screwdriver, you could get a shock. An example of a capacitor you might think of is a flash photography. When you take a picture, the battery charges up your capacitor, which is part of your light bulb. That's a pretty slow process, but when you press the button to take the picture and the flash goes off, that's a fast process. And so that's a place where a capacitor shows up in a circuit. One interesting idea that we'll talk about too is how exactly does a capacitor store energy? And I think actually that's a really neat question. You might never have wondered before, how does gravitational potential energy work? And electric potential energy is kind of the same. Elastic potential energy is actually fairly easy to understand. If you have a spring or something stretchy like a bungee cord, the energy is stored in those molecular bonds that get pulled apart. With gravitational potential energy and electric potential energy, the energy is actually stored within the field itself. So that's a neat idea too, which we'll talk about, but we'll cover the basics of a capacitor and how it works in a circuit first. Let's start with a really quick recap of a circuit diagram. So circuit diagrams are just diagrams that show elements of the circuits. Most circuits, lots of circuits, some circuits will have a source, and that means a source of potential. The source pretty often is a battery, and it has an amount of potential. The potential can have different symbols. Sometimes it's V, sometimes it's delta V, and sometimes it's epsilon for EMF. So the potential of a battery is measured in volts, and generally we're going to use the symbol V or epsilon. And then in a circuit, the battery supplies the potential. The potential gets used up across some sort of a load, and in this circuit diagram, the load is a resistor. So a resistor more or less uses up energy. It emits energy as heat. The energy is dissipated. We would draw this circuit diagram. We replace the battery by a couple of lines, a long line and a short line. The long line indicates the positive end of the battery. The short line is the negative end. And then resistors we replace with a zigzag line. So this is the circuit diagram to go with our above sketch. So the potential of our battery we might call epsilon. That has units of volts. So this is our battery. And this is our resistor. When we hook up a battery to a closed circuit, we get a current flow. The direction of a current flow is from positive to negative. So the current flows out of the top end of the battery, the positive end. Of course, with what we know now about current, it is actually electrons that move around. It's the negative charge. But back when they defined current, they didn't know about electrons. So current got defined as the direction of the flow of a positive charge. And then that got fairly well entrenched into the books and nobody wanted to go back and change it. Current has units of amperes, which I'm pretty sure is supposed to have an accent on it, but I can never remember which way. Sometimes that's called amps, and the symbol for amperes is an A. Our resistor is defined by a quantity R for resistance. The symbol or the units for resistance are ohms, and that has a symbol of a capital letter omega. What else do we say here? So the potential or the energy is supplied to the circuit by the battery. The energy is dissipated with a resistor. And we use Ohm's law in these kind of circuits that say that the potential across a battery is equal to the current through it times the resistance of the battery. So the potential and the current are proportional to each other, and the constant of proportionality is the resistor. This is, of course, Ohm's law. Let's label that. He's probably not the only guy who ever noticed that, but he is the one who made it into the books. So that's a recap of stuff you probably know about circuit diagrams with resistors. We're going to circle back around to those, but we're going to talk about circuit diagrams with capacitors in detail first. Next, we'll introduce capacitors to our circuit diagrams. As a reminder, a capacitor is what you get when you have two conducting plates, each with an area A, separated by some small distance d, and the charge density on the plates are equal and opposite. So let's draw in that distance d on our picture. So there's d. It's very exaggerated in this picture, but very important to remember is that D is small compared to the size of the plates. So the charge density on the plates is the charge divided by the area of the plates. What else? We know that the electric field between the plates of the capacitor is sigma over epsilon naught, and the direction of that field is from the positive to the negative. We know that the electric field outside an ideal capacitor is 0. And the last little bit that we'll add is that the space between a capacitor, it might be empty, might be just a vacuum, or it could be filled by something that we're going to end up calling a dielectric. So this space here, it might be empty or it might be filled up by something. So let's add a note for that as well. Space between the plates may be filled or empty. On our circuit diagrams, we're going to represent a capacitor by two little straight lines. This slide is a bit full, so we'll do it on the next slide. In our circuit diagram then, the battery is still represented by that long line for the positive and that short line for the negative. The wires of our circuit are just straight lines. Those are assumed to have no resistance. And then the capacitor is represented by two parallel lines. So that's what it looks like in a circuit diagram. This is the capacitor. This is not a bad place to stop and think about how a capacitor works. What happens when you hook it up to a battery? So we take we take one plate of the capacitor and we hook it up to a battery. And we take the other plate and we hook it up to the other end of the battery. So the one plate goes to the positive, one plate goes to the negative. What happens is that inside your battery, there's a chemical reaction. Okay, and that's how a battery works. That chemical reaction causes a positive charge to come out of the terminal and flow. So we get our current flow. When the positive charge hits this plate of the capacitor, it has to stop. It can't go anywhere because there's a big gap between the two plates. So it stops here. Then we ask what happens on the other plate. Well, the thing that happens on the other plate is all the positive charges on this plate are repelled by the positives on the top plate. So the positives move off that plate and move back around the wire until they get back to the battery. If all the positives are gone, then the net charge on that capacitor becomes negative. So that's more or less how a capacitor works. So you hook up the battery, the charge starts to flow. There is a limit to the amount of charge that flows, and that limit is set by the maximum potential on the capacitor is going to be equal to the potential of the battery. So when our capacitor is fully charged, it starts with no charge, then we hook it up and it starts to get charged up. When it's fully charged, the potential of the capacitor equals the potential of the battery. And then the other kind of neat thing that happens is once the capacitor gets charged to that full potential, the current stops flowing because it's fully charged. So no more charge is moving around anymore. So that's an interesting difference between capacitors and resistors. So let's talk about how do we characterize a capacitor. We know that batteries have a voltage or a potential. Resistors have a resistance, which describes the relationship between the current and the potential. What do capacitors have? Well, we say that capacitors have capacitance, and we represent that by a capital C. Capacitance is a C. Heads up here, be careful between C for capacitance and C for coulombs. I know it's a small thing, but it's easy to get this stuff tangled up in your head. Okay, so C is our capacitance. That's the characteristic of a capacitor. We'd like to be able to figure out what is the capacitance. So let's think about what happens. Our capacitor is two plates. They each have area A and they're separated by a distance D. So the distance between our two plates is D. A battery charges up a capacitor until there's a potential difference of V between the plates, and each plate ends up with an equal and opposite charge density. So one plate becomes positive, one plate becomes negative through the process we described before. So this plate has charge plus Q, this plate has charge minus Q, this plate has a charge density sigma, which is the charge over the area. This plate has charge density minus sigma, which is minus the charge over the area. Okay, so the separation of charge, well, first of all, let's say about the net charge. The total charge on our capacitor is 0. There's plus Q on one plate, minus Q on the other plate, add them up, you get 0. But there is a separation of charge. If one is positive, one is negative, it means that there's going to be an electric field between the plates and it points from positive to negative. In our work on Gauss's law, we found that the expression for the electric field between the plates was given by sigma over epsilon naught from positive to negative, plus to minus. And epsilon naught is our constant 8.85 times 10 to the minus 12. This means that the magnitude of the electric field between the plates is sigma over epsilon naught, and sigma is our charge density, so we can write that down as Q over A times epsilon naught. So that's a recap of the electric field between the plates. If there's an electric field between the plates, then there's going to be a net potential difference between the plates. So the potential difference between the plates is going to be V, or delta V, equals the strength of the field times the plate separation. So, we can find that expression for potential by doing the integral of E dot ds, which we went through in a previous class. So let's fill in what we mean by our electric field. That's Q times A over epsilon naught, and this is times D. So this tells us that our charge Q, I think I'm not going to have quite enough room right there. So our charge Q is equal to A times epsilon naught divided by D times the potential V. This shows us that our charge on either plate is proportional to the potential across the plate, and the capacitance C is the constant of proportionality. This slide is a little bit full, so I'm going to write those notes on the next slide. Let's write down our conclusion now. The charge is proportional to the potential. The constant of proportionality is what we call capacitance. So C is A, the area of the plates, times epsilon naught, our permittivity of free space, divided by D, the distance between the plates. Okay, first interesting thing is that capacitance just depends on the physical parameters of the plate. That's kind of interesting. There's a hint in here about our capacitance too. You see that the capacitance depends on epsilon naught. That's the permittivity of free space. So the capacitance depends on what's between the plates as well. And we'll get to talking about what's between the plates. What else will we add? The units of capacitance are called farads, after Michael Faraday. Farads has a symbol of F, which is equal to a coulomb over a volt. You can show that that's the same as coulombs squared over joules. I'm going to leave that for a homework exercise. By showing that it's equal to coulombs squared over joules tells us that capacitance is related to energy. And that makes sense because if our capacitance is charge over potential, and potential is potential energy over charge, then energy is tied in there with our potential. So that's pretty interesting. And then capacitance is a measure of the ability of a capacitor to store energy. So that's what capacitance is. It's a measure of how well a device can store up energy. Maybe the last thing we'll say here before we move on, we're not going to do any work on this, but it is kind of interesting. In some capacitors, maybe even most capacitors, the plate separation D is a constant. But in some capacitors, D is actually a variable. That means that the capacitance is variable, and an example of that is a condenser microphone. So sound waves are emitted, they hit the microphone, and it vibrates a plate called a flex plate that changes the capacitance, makes a charge flow. That means that the sound waves get converted to a current that's amplified and then recorded digitally. So that's kind of an interesting application of a capacitor. Here's a couple of really straightforward homework questions for you to try. If we know the charge on a couple of plates and the potential across the plates, can you find the capacitance of the electrodes? And then second is to show that the unit of capacitance, a farad, is the same thing as coulombs squared over joules. I won't include these in the video, but I will post solutions for you to check your answer against mine. Let's use an example now to get a size of a scale of a farad, like kind of what does a farad mean? So let's say we have a parallel plate capacitor. It has a capacitance of 1 farad. The plates are 1 millimeter apart. That's not atypical. It can be smaller, but 1 millimeter certainly does happen. What is the area of the plates? So what is A if that's our capacitance and that's our plate separation? We remember that capacitance is epsilon naught times A over D. The capacitance depends on the physical properties of the plate. That tells us that the area of each plate is D times the capacitance divided by epsilon naught. So D is 1 millimeter. The capacitance we said was 1 farad. Divide that by epsilon naught, which is 8.85, times 10 to the minus 12. Now, for units, let's go on a small sidetrack about units here. Epsilon naught is the permittivity of free space. It's 8.85 times 10 to the minus 12 coulombs squared over newtons times meters squared. Here we might recognize that coulombs squared over newtons times meters is a farad. So coulombs squared over newtons times meters squared is the same thing as a farad over a meter. Okay, it's always, kind of going back to basics, thinking about units is always an important step in every problem. When we run this through the calculator, what we get is 1.13 times 10 to the 8 meters squared. So let's pause and take stock. Is that a sensible size for a capacitor? If those plates were square, they would be 10.6 kilometers on a side. I would have to say, no, that's not the least bit sensible. So my conclusion here is that 1 farad must be very large. And in fact, typically, capacitance run on the scale of a microfarad to a picofarad. So usually we go from the scale of microfarad, or 10 to the minus 6 farads, to a picofarad, where pico is 10 to the minus 12. And in the homework example we had, it was a nanofarad. So normally capacitances we look at are going to be in the range of somewhere between 10 to the minus 6 and 10 to the minus 12 farads, and that's going to be a reasonable value. Now, the next thing we're going to segue into our next part is our epsilon naught in our capacitor equation. So here in our capacitor equation, capacitance is epsilon naught times A over D. Epsilon naught, the permittivity of free space, describes how an electric field travels through a vacuum or through air, because air is fairly close to a vacuum. If we put something between the plates, so in this capacitance example, we have 2 plates just separated by air. If we put something between the plates, we wouldn't use epsilon naught anymore because the electric field is not going through air, it's going through the stuff. Then instead of using epsilon naught, we would use epsilon, which talks about how electric field goes through stuff. And the stuff we put between the plates is called a dielectric. The benefit to this approach, before we get into the treatment of it, is just think for a moment, if you scuff across a carpet, you get close to a doorknob and you touch it, you get a spark. That little spark of electricity is what happens when you have a high potential separated by a small distance. You get a large electric field. The air, if you have a large electric field, the air actually breaks down and current flows through the air. That's the spark. It's a current flow from you to the doorknob. That sort of spark, it's fine when you're touching a doorknob, even if it's not pleasant, but it's less fine when you have a capacitor in a circuit. So if you have those large electric fields in your capacitor can have a spark, which can cause it to burn. That is very bad for your device and for your circuit. So what you can do is put something between the plates to reduce the effect of that breakdown. That's the next part we're going to get into now, is talking about the stuff between the plates.